Hi and welcome back. So we're going to start continuing on with our look at HL reaction kinetics, which we started to look at in class. So we'll go through what we talked about in class again. Hopefully it will become clearer, and then we'll move on to part 2 where we talk about order of reaction a little bit more and working out the reaction mechanism based on rates data. So let's get started. So rate expressions and rate law for a reaction, are a way for us to express mathematically what's going on with rate of reaction in a more full way. So the rate expression is a quantitative analysis of how concentration of the reactants and initial reaction rate are related in the reaction. So we know that the rate decreases over time as the concentration of the reactants decreases because the number of collisions, therefore the proportion of successful collisions, will decrease. But we can mathematically describe that a little bit more, as we saw with SN1 and SN2 reactions, that the rate of reaction is not always dependent on both reactant concentrations. Sometimes it's only dependent on one. Sometimes it might not actually be dependent on the concentration, but something else within the mechanism of the reaction. So we can say that the rate of any reaction is expressed in terms of the concentrations of a reaction. So the rate, remembering that this will be in units of concentration per unit time, is equal to a constant K, which we will define as the rate constant, multiplied by the concentration of reactant A raised to a certain power, B raised to the power of y, and c to the power of z. When we define each part of this expression, we get that K is the rate constant for a particular reaction at a specific temperature. So again, just like equilibrium, we are talking about a particular reaction at a particular temperature. If we change the reaction or we change the temperature, K is no longer constant. Then X, Y, and Z are what we refer to as the order of the reaction with respect to that reactant. So we have the concentration of reactant A with its order with respect to A, B with its order with respect to B, and C with its order with respect to Z. So this gives us the rate expression. And we need to start looking at these mathematical ideas of rate in order to be able to determine the order. So as we said, K is a constant, and it's basically a proportionality constant. It is a multiplicative factor between the reaction rate and the concentration. It is independent of the initial concentrations, so unlike the rate of reaction, which we know is fastest at that initial concentration, K is independent of the initial concentration of the reactants. So it's not affected by the concentration of the reactants. It remains the same when a reaction is carried out using different starting concentrations. So K for a reaction at a given temperature is independent of concentration. It is a ratio. So as we said, much like the equilibrium constant, it is not really a constant because it can be affected by a number of different things. Like equilibrium, K is affected by temperature, but it is also affected by the presence of a catalyst and the state of the matter of each of the reactants. So whether it's a solid, liquid, or gas. All of these things will affect the collision frequency and the energy in the system, and that will affect K. So the unit of K changes dependent on the overall rate law, so dependent on this expression that we get here, which is our rate law, the units will change, much like the units of equilibrium change. So the greater the K for the same concentration of reactant, the faster the reaction. The greater the K, the greater effect of a concentration change on the rate of a particular reaction. Remember that this is a proportionality constant. So if we look at this reaction, this is what we described and graphed rate as from SL. We can see that rate is maximum at the start of the reaction. We have the maximum greatest gradient. If we calculate our gradient, our rise over our run, we can see that early on we will have a much greater rate of reaction. and that they will parallel each other. Okay, as the rate of the decomposition of the products decreases, we have an increasing rate of the formation of the products. Okay, so we essentially looked at this in SL for allowing us to graphically represent a rate of reaction. So from this, though, we can start to determine the rate expression. In order to do this, we need to be able to graphically describe a reaction. And in this case, we're going to set up a set of data, okay, that is essentially made up. We're going to set up a hypothetical set of data. So if we look at this reaction here, we have acidic solution reacting hydrogen peroxide with iodide ions reacting with H+ to form iodine and H2O. It was set up and the iodine concentration was measured at various time intervals using colorimetric analysis. This is measuring the intensity of color, which we can do because iodine is a colored reagent. So just like bromine, the ions are non-colored, but the halogen itself in its diatomic form will be colored. So the color will increase as this reaction progresses to produce more products. We're starting with an initial concentration of peroxide of 0.5 and everything else is in excess, which means that our limiting reagent is the hydrogen peroxide. Because everything else is in excess, their concentrations can be considered constant because the change in concentration won't impact the rate. Okay, and it's not going to change negligibly during the reaction. So we want to find the relationship between the reaction rate and hydrogen peroxide concentration. So by keeping everything else in excess, then it's only going to be the concentration of hydrogen peroxide that affects this. So we set up a data table. The concentration of hydrogen peroxide remaining was deduced from the concentration of iodine present. Remember, this was monitored using the fact that stoichiometric reacting ratios is 1:1. So for the measured concentration of iodine, then we know that because it's 1:1, the concentration of H2O2 is going to be our initial concentration of the hydrogen peroxide minus the amount that will have reacted, which will be equal to the number of mole of iodine. So as we measure the concentrations of iodine over time, we generate this data here, and from that we can assume that this is the change in concentration of our hydrogen peroxide. So we can only measure the iodine concentration, and then from that we are deducing the hydrogen peroxide concentration. Once we have that data, we can now generate the graph to be able to interpret it. From this graph, we are seeing the change in concentration of hydrogen peroxide with respect to time. Again, this is a standard rates graph that we should be used to seeing from SL. And we can determine the rate in terms of moles per decimeter cubed per second by using the graph and calculating the tangent to the curve at a particular point in time. Okay, so from this we can see that the rate is maximum at the start, then decreases due to the decreasing number of particles that are available to collide with sufficient energy greater than or equal to activation energy and lower the rate of reaction. We need a negative sign because it's a decomposition reaction, so the concentration of H2O2 is going to decrease over time. Okay, and we want to find the relationship between the concentration and rate. This means that we need to compare different concentrations and different rates, and then use a graph to find a few different rates and plot these two. Okay, so what we want to do is generate more data in order to be able to plot this. So if we take the time, so these are our time intervals again, we have our concentration of H2O2, okay, and then from our previous graph we have worked out the rate at different times and different concentrations, and then we can plot the concentration versus rate. When we do this, we can see that the rate is proportional to the change in concentration of H2O2. We get a linear relationship, so we mean the rate is increasing as the concentration of H2O2 increases. This is a linear relationship. Okay, so they are proportional to one another. This leads us to order of reaction, in that the order of reaction that we saw introduced in the idea of the rate expression earlier indicates this relationship between the concentration of the reactants and the reaction rate. The order of reaction with respect to a specific reactant, remember we said A to the X, okay, is the power to which the concentration is raised in the rate expression of the rate law. So for any reaction with respect to a single reactant, the rate will be proportional to the concentration of the reactant, where N is the order of the reaction. In this course, we will look at values of 0, 1, and 2 with respect to the reactants in a reaction. Okay, so we refer to these as 0, first, and second order reactions. Each of these has a different mathematical relationship. If you can imagine, if we have a reaction that has reactant A and it is a 0 order, anything raised to the power of 0 is going to equal 1. So the rate will not change if the reactant concentration is changed. So the rate is constant with respect to this reactant. If we have the reactant now being raised to the power of 1, this is a first order reaction. This is telling us that the rate is directly proportional to the concentration of this reactant, as we saw with the hydrogen peroxide in the previous example. So if we triple the concentration, we will triple the rate. Okay, it's a direct linear relationship. This is a first order reaction. In the case of a second order reaction, the rate is proportional to the concentration squared. So the value of N is 2, so we are now raising our concentration to the power of 2. This means that the rate is directly proportional to the concentration squared. Doubling the concentration will increase the rate fourfold. Okay, because we double the concentration, so it's 2 to the power of 2, that's going to be fourfold. If we triple it, it's going to be 3 squared, so that's going to be 9. So this, if we double the concentration, it will be a fourfold increase. If we triple the concentration, it will be a 9-fold increase in the rate due to this squared proportionality. So, as I said before, this gives us the order with respect to each reactant. The overall order of the reaction is the sum of the orders with respect to individual reactants, and the individual reactants in a reaction can have different orders. We saw this with SN1 and SN2, okay, where we talked about the formation of the carbocation. The reaction, the slowest step is going to be that. It doesn't matter about the concentration of sodium hydroxide as long as the rate determining step is the formation of the carbocation. So for the overall rate expression, we have the rate is equal to K, A, concentration of A raised to its order, concentration of B raised to its order, and then the overall order of the reaction, this would be 3 for this one. We're going to add the indices. So for a first order reaction, and I recommend you just learn these, if the reaction is 0 overall, it is independent of the concentration of the reactant. So the rate will always equal K, and the units will be moles per decimeter cubed per second. If it is a first order reaction overall, the rate will equal K multiplied by the concentration of the reactant, and its units will be S to the -1. If it is second order overall, the rate will be equal to K multiplied by the concentration of A multiplied by the concentration of B, and you will have moles per mole decimeter cubed per second. Third order overall will be rate is equal to K multiplied by the concentration squared, and B multiplied by the concentration of B, mole to the -2, dm6, s to the -1. Okay, so these are the standard expressions and units where you have a 0, first, second, and third order reaction overall. Remembering that the overall order of the reaction is given by the sum of the indices from the rate expression. Okay. When we come to graphing order of reaction, we need to pay close attention to the units. There are two main types of graphs that we will be seeing in order to determine rate laws. We will see a concentration of the reactant being investigated versus time, which is a standard one that we have seen. Okay, so this is a standard SL rate curve where the concentration of the reactant is going to decrease over time, okay, and then the rate of reaction is the curve to the tangent to the curve. Okay, so we can measure the rate by measuring the product over time or the reactant over time. When we do product, it will be the increase in product over time. When we're talking about reactant, it will be the decrease in reactant. So we can calculate the rate by taking the tangent to a curve as an instantaneous rate, or we can get an average rate. Generally for these, we want to get an instantaneous rate at different intervals so that we are then able to plot the rate versus concentration change. Okay. If we have a look here, we have the concentration of N2O5 versus time, and this is decreasing over time. If we then calculate the rate by taking a tangent at various instants and plot that rate versus the concentration, okay, so if we work out the instantaneous rate at this concentration and then plot that, the shape of the graph will tell us what order it is. Okay, but we need to plot rate versus concentration in order to be able to determine the order from the shape of the graph. So a zero order will be a straight line, okay, when we have concentration versus time. The concentration of the reactant decreases, but the rate of the reaction remains the same. The gradient is constant. Okay, so the change in concentration of this reactant doesn't affect the rate of reaction. So we have a linear relationship here. So we have a decreasing curve. We have a negative curve that stays straight because it is a direct proportionality, i.e. the rate is not changing. The gradient is constant. If it's first order, we'll have an exponential curve downwards. And then remember, this is a concentration versus time graph. So zero order, we're going to see this. First order, we're going to see an exponential with its curving downwards. Second order, we're going to have an even steeper curve downward because of the greater relationship between concentration of the reactants. So the downward curve is steeper than the first order, and the rate decreases more rapidly as the concentration of the reactant decreases. Okay, so rate decreases more than the concentration of the reactant. So it's not always easy to notice first order and second order when you see the graphs independently. You need to sort of see them next to each other. So this is a rate versus concentration graph. So this is slightly different in that now what we're looking at is not a concentration versus time. This is rate versus concentration. So in this case, we can see that this is a zero order because the rate does not change with changing concentration. So it is constant. Here we have a first order because the rate and the concentration are directly proportional to each other. If I increase the rate, the concentration increases by the same proportion. And then this is going to be a second order because I have an exponential relationship. The rate will increase fourfold by an increase in concentration due to the squared nature. So we're going to have it squared each time I change the concentration. Okay, I know this video is long, but bear with me. Feel free to watch this in a couple of parts. When we remember everything we do with rate is typically experimentally determined. We can use a discontinuous method, so the rate of reaction is followed by measuring the concentration of the chemical iodine during the reaction by colorimetry. We can use a concentration time graph for each reactant in each experiment where its concentration is changed, is plotted, and the initial rate of reaction determined. Okay, going back through zero. The effective concentration change of each reaction is determined. Once the rate expression has been established, the rate constant can also then be calculated. Okay, if we use the continuous method where possible, okay, we map the concentration change of each reactant and we follow this during the reaction, and a concentration time graph is drawn automatically. You might be able to do this with a data probe. Okay, it is preferred as it reduces the error in this method, but it's not always possible. We can't always, like with the iodine clock reaction or with the sulfur precipitation reactions, we need to test concentrations independently. We aren't able to continuously change the concentration over a particular period of time and still get the data. So while continuous is desirable, it's not always possible. One of the most common ways that you're going to see this presented to you is in a table of data. You will have a series of experiments. This is experiment 1, 2, 3, 4. The reactants for these experiments and the concentrations of those reactants for each trial, and then the rate that has been measured for the initial rate for each of those concentrations. What you want to do with these is you want to be able to find the ones, remembering if it is a zero order, the rate will not change with a change in concentration. If it is first order, if we double the concentration, the rate will double, so the proportionality is the same. If it's second order, we're going to have that squaring effect. So what you want to do is find a concentration of a reactant is doubled and the others remain constant and see what happened. So if we have a look here, in this one, the reactant A is doubled and B and C remain constant. So when the concentration of A is doubled, we see that the rate is doubled. Therefore, this reaction must be first order with respect to A, because as I doubled the concentration, I saw a doubling of rate. I can then have a look here where we want to compare some others. Okay, when B is doubled, okay, so between 3 and 1, okay, so here these two are constant, these two are constant, and then I have 0.8 to 1.6. So going up to here, I have doubled the concentration of B, and I see that the rate is constant in this case, which means that this is, in regards to B, this is a zero order reaction, because when we altered the concentration of B, the rate did not change. Then the one that we need to do is look at trying to find one where we have C. In this case, we can see that C is going to be 0.06 to 0.18, so we're going to multiply by 3. We need to find one where it's constant for the others, so we're going to pick trial 2 and 4, because the concentration of A and B is constant here, and this time it's tripled. And we can see here that the rate between this point, this point and this one, 9.72 to 87.5, this is, if it was tripled, then we would expect it to triple, okay? If it's doubled, okay, we would expect it, if it's second order, we would expect, if the concentration we've got tripled, we would expect it to be times 9. Okay, so if we look at 9.72, we're going to see that this is actually a times 9 difference, and 3 raised to the power of 2 is equal to 9. So this is actually, with respect to C, it is second order. So when we write our rate expression, our rate is going to be equal to K multiplied by the concentration of A, because it's A to the 1, which is itself, multiplied by the concentration of C squared. We exclude B because it has no effect on the rate. Okay, so it doesn't get included in our overall rate expression. So for this, we have a reaction that is first order with respect to A, zero order with respect to B, second order with respect to C, and the overall order of the reaction is going to be third order, okay, because we're going to add 2 and 1. So the overall order of reaction is a third order reaction. So breaking down our rate law and rate expression, okay, they mean the same thing. The rate of the reaction in moles per decimeter cubed per second is given by the rate constant, whose units are variable, multiplied by the molar concentration of reactant 1 raised to its order, multiplied by the molar concentration of reactant 2 raised to its order, where the order can equal 0, 1, or 2. Okay, the overall order of the reaction is the sum of those indices. So it is important to note that you can't predict the rate equation for a reaction from its balanced equation. The equation itself gives us no information about the rate. In order to find out the order of the reaction, we must carry out practical experiments where we change the concentration of one reactant, keeping all others constant, and seeing what happens to the rate of reaction. Does it stay constant, therefore zero order? Does it change by the same factor that we change the concentration, therefore first order? Or is it a squared relationship? So if we double it, it goes fourfold. If we triple it, it goes ninefold. Okay, we need to collect this data experimentally in order to determine the order of reaction and use graphical techniques in order to figure this out. So to find the rate expression, we figure out the order of reaction with respect to each reactant using experimental data. We write out the expression using the rate law is equal to K, A to the A, B to the B, where A and B are of the order of reactions determined by the experimental data. We sub in the values from the experimental data to find the value for K, remembering that K will change dependent on temperature or if there's a catalyst or the state of the reactants. Okay. As we said, the overall order of reaction is the sum of the order of each component in the rate law. So if there's 3 reactants, then we sum the order for each reactant. Okay, so in this case, for this reaction, when we have K, H2SeO3, this will be a first order because the 1 is implied, H plus with a second order, and then I minus being third order. The overall order of this reaction would be 6. We just sum the indices from the rate expression. Units of K are complicated, as I mentioned before. When you calculate K, you need to multiply and divide the units for rate and concentration. In all honesty, unless you're particularly comfortable with working out units, I would recommend memorizing these units for your first, second, third order reactions and your zero order for values of K. So just finishing out this very long video with an example calculation of K. In this case, the reaction has the rate expression where the rate is equal to K A squared B. okay? And we've been asked to calculate the value of K, indicating the units for the reaction when the concentrations of A and B are both 2.5 times 10 to the negative 2 moles per decimeter cubed, and the reaction rate is given as 7.75 times 10 to the negative 5. We have been given the expression, so we are simply going to substitute in rate 7.75 times 10 to the negative 5, and we're keeping the units in here, excuse me, is equal to K, which is what we're looking for, multiplied by the concentration of A squared, multiplied by the concentration of B. So this means that we are going to have moles per decimeter cubed, working out our units, and then 2.5 times 10 to the negative 2 cubed as well, because essentially this is the same number, so it's going to be cubed. And then on our top line, we're going to have 7.75 times 10 to the negative 5 moles per decimeter cubed per minute. So when we work this out, we're going to end up with mole to the neg 2 decimeter to the 6, minute to the negative 1, because this one's our unit of time here. And when we do this, when we plug it into the calculator, we get 4.96. So these calculations of K are all simply going to be substituting in and solving for them. The trickiest thing is going to be determining your order of reaction, and typically you will see that from the table of data that we saw earlier. Okay, that's it. I know this has been an epic video. Make sure you go through the questions on the handout and you will see that these are a little bit simpler than what the whole explaining it makes it appear. Okay, what you need to be able to do is understand you really need to be able to understand the graphing of these, so the shape for first, second, and zero order reactions when we're talking rate versus concentration, and the shape of graphs for the concentration versus time, and then how to substitute these values in. We'll have a bit of practice in class. Hopefully you're not feeling too overwhelmed, and I'll talk to you later.